Welcome! It's time to talk about tangent planes and linear approximations. So let's start with something really conceptual. What is a derivative? Now, you may be thinking a derivative is a tangent line. You may be thinking it's f of x plus h minus f of x over h and limit. You might be thinking it's the power rule or the chain rule. But what it really is, geometrically, it is the best linear approximation of a function near a given point. So that is to say, can we find a line that is, for instance, very similar to the function sine of x near x equals pi over 3? Well, let's go over how we would do that. So what we would do is to say, we'd have a function f of x equals sine of x, and x is pi over 3. Now we can get first a point if we just plug in pi over 3. We get sine of pi over 3 is equal to root 3 over 2. So we'll get what I call an anchor point. I don't know if there's a technical name for this, but I think of it as what the point where your approximation is stuck to your regular graph. And so that would be x is pi thirds, y is root 3 over 2. So we know one point for sure, but what if we start moving away from there? Well, we think that sine probably doesn't just jump hugely. If we pick x, it's close to pi over 3, y is probably close to root 3 over 2, but it would be helpful if we know how fast it's rising as we go away. And so what we can do is we can take a first derivative. F prime of x is cosine of x. And then we will plug in that same pi over 3 there and get 1/2. So what that means is not only do we have a point to start at, but as we go away from that point, we will go at a slope of 1/2. So what would we do then? We would say, if we remember back to how we did this in calculus, it was y minus y naught equals m x minus x naught. And then we'd plug in the different parts. The anchor point would be y minus root 3 over 2. The m, the slope, is 1/2 x minus pi over 3. That is our line, and it is our best approximation. Let's get a picture of what that looks like. So we'll go to Desmos this time. And if I graph y equals sine x, and then I also graph y minus square root 3 over 2 equals 1/2 x minus pi over 3. And what it says is, if we look at our anchor point, which was pi thirds and root 3 over 2, that is right about here. Pi is 3.15 or so, and so pi over 3 is about 1.047. And we see that near there, it's almost exactly a line. As it goes farther away, then it turns into something else. So the linear approximation is good as long as we don't go too far from that point, that anchor. And in fact, it is the best line that could possibly be used there. So this gives us the actual definition of what a derivative is. We say a function is differentiable at some point if we can write as y minus y naught equals m x minus x naught plus epsilon times delta x. So what this epsilon thing is it's a correction. It's saying this first part here, that's a line. And it's not exactly the same as the line. We have this other function, which could be extremely complicated, that corrects it. But the limit when delta x goes to 0 of this is 0. Meaning that the closer we get to x and x naught being the same thing, because delta x is just x minus x naught, the smaller that difference gets, the more accurate this estimate here is. You could write this as delta y equals m times delta x if you wanted. So what would it be in 3 dimensions? Well, the appropriate object here would be a tangent plane. And so if you'll think back to your 3D models, imagine you were to try to lay a piece of paper on one of them so that like a stiff note card or something that doesn't bend, and if you were to just lay it on at one point, it would be approximately equal to the surface as long as you didn't go too far away. So we use the same basic setup. The equation of a plane is z minus z naught, or delta z, equals a x minus x naught plus b y minus y naught. And then there are 2 corrector functions, these 2 epsilons that are based on delta x and delta y. And again, we don't usually know what these are. They're probably quite complicated, but we know that if we let the delta x and delta y shrink, they vanish. And so this is the equation of the tangent plane. Z minus z naught equals a x minus x naught plus b y minus y naught. The only question is, what are a and b? And it turns out to be simpler than you might be worried. See, if we have a point, let's say x minus x naught, or sorry, what did I say? X naught minus y naught is what I meant to say. I did not mean that. X naught comma y naught. I'm not speaking clearly. We have x naught y naught, and if we come from the side, y equals y naught, along that path, it will zero out. And so along that path, we just get z minus z naught equals a x minus x naught, because the y minus y naught disappears. We then take the partial z over partial x would equal just a. Because if we take the partial derivative on the right, x goes to 1, x naught goes to 0, so the partial derivative at that point is the coefficient for the x and the x naught, the x minus x naught. And the same true for the b. So what we're saying here then is you take the derivative fx and you plug in the point, that's your coefficient for x minus x naught. And for y, you take the derivative with y and plug in the point, the anchor point, x naught, y naught, times y minus y naught. And that's your tangent plane. I want to warn you that the a and b are constants. I will see people do this all the time. They'll take the derivative and it'll be some really long expression, and they'll write that entire really long expression. But no, this is a plane, which means a plane is linear. It is the 2-dimensional version of a line. And so we need the coefficients to be constant. So you take the derivatives and you plug in the anchor point to get their values. So here is the process in words. If you are asked to find the tangent plane near a point, take partial derivatives, fx and fy, plug in the anchor point, x naught, y naught, z naught, to the partial derivatives. Sometimes you won't need to plug in the z naught because it'll only have x and y in it. Sometimes you will. Then you can write the parent function equation, which is this. Z equals f sub x, plug in the anchor point times x, f sub y, plug in the anchor point times y. This step you usually skip. It's just saying this gives you a plane that's parallel to the right one, and then you shift to the anchor point. So this is the form you would actually want. Z minus Z naught is the derivative of x, plug in x naught, y naught, and Z naught if it's necessary. It's a little inconsistent. I should have a Z naught here as well. And plug in the fy, x naught, y naught, Z naught as well. All right, let's go ahead and do an example. Find the tangent plane to the surface z squared equals 2x squared plus y squared at the point 1, 1, 3. So, how do we do this? I'm going to go ahead and open up our graphing because I'm going to want to look at the graph when we get the chance. So let me go ahead and open that up. But let's start off by doing it algebraically. So our function was z equals 2x squared plus y squared at the point 1, 1, 3. So let's get the partials. Del z over del x would be 4x. Del z over del y would be 2y. So we'll go ahead and plug in the points 1, 1, 3. Now neither of these have a z in them, so we don't really need to worry about the 3. And so we get 4 for the first one and 2 for the second one. What is our anchor point? Well, it's this. It was given to us, 1, 1, 3. So the equation would be z minus 3 equals 4x minus 1 plus 2y minus 1. So z minus 3 is 4x minus 4 plus 2y minus 2. And we can collect like terms. And again, if it just says find an equation, you don't have to expand it out like this, but I'm doing it anyway just for, it looks a little cleaner, I guess. Z is 4x plus 2y minus 3. So let's go ahead and graph these and compare it. So it's z equals 2x squared plus y squared. All right. So where is it? Here we go. Z equals 2x squared plus y squared. And let me check the range. It was 1, 1, 3, so that should... All right, let's add in a second function, which will be the plane 4x plus 2y minus 3. Oh, what the heck? 2y. Excuse me, typo. So I use the zoom out button to, well, zoom out. And I can see now I marked the original equation, that's this cone-like thing, and the plane, and I marked the specific point, our anchor point as well. And if we look, see there it is, you can see as you look on, the plane and the surface are pretty similar there. It is sort of right up tangent to it. And we can zoom in some more. I think it just artificially separates it so we can see them both. But if this were perfect, it would be laying directly on there. All right. So let's do another example or see what's next. Okay. There is another form of the tangent plane equation that we can use. And it comes from the observation of the implicit functions we talked about a while back. And that was that we said that del z over del x is negative fx over fz. Del z over del y is negative fy over fz. So the equation we gave was z minus z naught is del z del x, x minus x naught, plus del z over del y, y minus y naught. Well, we can replace those partial derivatives with these expressions. Z minus z naught is, where is it? Negative fx over fz, x minus x naught, plus negative fy over fz, y minus y naught. And then multiply through by that fz, we would get fz, z minus z naught, equals negative fx, x minus x naught, minus fy, y minus y naught. And then move those negative ones over to the other side, and we get this new form. Fx, plug in x naught, y naught, z naught, times x minus x naught, plus fy, plug in the anchor point, y minus y naught, plus fz, plug in the anchor point, z minus z naught, equals 0. And this form is often more used for implicit functions. And if you're not familiar, implicit is like this, where we've got z's on both sides of the equation. An explicit would be we'd have z on one side, just z equals, and a whole expression. This is an implicit function because if we were given an x and y, we could plug in to solve for z, but we don't have an actual formula. So let's see how we can use this new form for implicit functions to get the tangent plane near 0, 1, e. So let's check that out. All right. So we will take the function we were given, z equals y e to the xy ln z, and we'll rewrite it as f of x, y, z equals y e to the xy ln z minus z equals 0. So if you want to use this implicit form, you've got to write it like that, as set equal to 0. I mean, maybe there are other ways to do it. There probably are, but this is the safest way, the way it doesn't cause problems. All right, so let's do f sub x. It will be, so let's do the first term, y ln z are all constants. Remember, when we're doing implicit, we pretend like z is independent of x, y, so we don't have to bother with the del z, del x whenever we see it. Then derivative here would be, well, let's just do it like this. Del over del x of e to the xy minus 0 equals y ln of z times chain rule here would be y e to the xy. So we get y squared e to the xy ln z. And now let's plug in our anchor point, 0, 1, and e. And that'll give me 1. Pause if you need to work that out, but it comes out to a 1. Let's do fy. That is ln of z times del over del y of y e to the xy minus 0, which would give me ln of z, product rule, 1 e to the xy plus y x e to the xy. And now we will plug in 0, 1, e. And this should also give us 1. And then fz would be y e to the xy is all a constant, and derivative of ln of z with respect to z would be 1 over z minus z, so its derivative is 1. Plug in 0, 1, e here. We will get 1 over e minus 1. Or if you prefer, 1 minus e over e. So, our tangent plane then would be, let's see, the vectors we got, the partial derivatives was like this. 1, 1, and 1 minus e over e. You can write them all as a vector like that if you want. There's a name for that. We'll talk about that next week. So then we will get 1 x minus 0 plus 1 y minus 1 plus 1 minus e over e z minus e equals 0. And if we want to expand this and collect some like terms, so it would be x plus y minus 1 plus 1 minus e over e times z plus e times negative e. Those divide out, and we get e minus 1 is 0. So x plus y plus 1 minus e over e z plus e minus 2 is 0. That would be the simplest form. Okay. So let's keep rolling. So what can we use this for? Well, okay, one thing I wanted to show real quick. It is possible for a function to have surface to have partial derivatives but no tangent plane. And that's where it gets really sharp. Let's see an example here. Let's go to the textbook. We are in section 14.4. All right, section 14.4. Back one. That's figure 3. They show a good picture here of how the tangent plane looks closer and closer as you zoom in. There's figure 4 that I wanted to show. Yeah, this is a case here where it's undefined at 0 and the derivative is real messy, so you get this really ugly thing with this sharp corner, and there's no way to put a tangent plane next to a sharp corner, so that's when we don't have a tangent plane and no derivative is when it has a sharp corner there. But we can say as long as the partials are continuous near the anchor point on some open ball, then there will be a tangent plane. So that's the test. Okay, so let's talk about linearization. So, what's this mean? Well, it's a way of estimating a function. Now, some of you might be thinking, why do we need to do that at all? I've got a calculator. I'll just plug it in. And I'm not going to say, oh, you won't always have a calculator with you. I mean, that's not the world we live in. But what I am going to say is that a lot of you, especially you computer science people, you might be the ones programming these calculators. So, if you were to give a calculator this problem, find f of 1.1, negative 0.1, what is it actually going to do? Because all calculators really can do is they can add and multiply. That's what they're good at. So what would it do here? My first calculus professor worked at Texas Instruments, and he explained all this to us. E to the negative 0.11. Do you think the calculator just has a table that has thousands upon thousands of entries and would take terabytes of data to hold? No. What it does is it will use some sort of series. For instance, it might use the Taylor series. So this is 1 plus negative 0.11 plus negative 0.11 squared over 2, which would give you 0.985655, which is a decent approximation. The one they give, this is something that really bugs me in a textbook. They will say, what is the exact value? Well, it's an irrational number. Its exact value has infinitely many decimals. If you type into a calculator, you get 0.985417548. That's what I get, but it keeps going depending on how advanced your calculator is. This is a pretty good approximation of that, but what did we have to do to get here? We had, how many multiplications do we have to do? We did one multiplication, and a second multiplication here to square, a division, which counts another multiplication, and then yet another multiplication. That was 4 multiplications. And also 2 additions. Sometimes these are measured in flops. I'm not sure exactly what a flop is, but it has to do with how many operations are needed. So it had to do 4 operations to get this decent estimate. And think about if you're programming something that has to do thousands upon thousands of these, just how much processing time that uses. So what if, instead of using this function itself and to use some sort of series expansion, we just use a linearization. We just use a tangent plane. Well, let's see how that would work. All right, so we were looking for the point 1.1, negative 0.1. So we need to choose an anchor point, and the anchor point needs to be one that we can plug in to this function or to its derivatives. So we'll just pick a point close to this. Anchor point will be 1 and 0. We'll just round these off to the nearest easy numbers. And what would the z value be here? If I plug in 1 for x and 0 for y, I get 1. So that's my anchor point. So let's do the derivatives. Del z over del x here would be, okay, this is a product rule problem, 1 e to the xy plus x, and then derivative of this would be y e to the xy. Then we'll plug in 1, 0, 1. Again, there's no z in here, so we don't really need the last 1. So if y is 0, this term goes away, so this will just be 1. And if I plug in del z over del y, would give me x squared e to the xy. Plug in 1, 0, 1 here, I also get 1. So the function would be z minus 1 would equal x, or sorry, would equal, I guess I'll write it anyway just to be safe. 1 x minus 1 plus 1 y minus 0. So z equals x minus 1 plus y plus 1 is x plus y. So if they said find f of 1.1 negative 0.1, well, we know that's near our anchor point of 1, 0, 1, so we can just plug in. It's about 1.1 plus negative 0.1, which is 1. Now that's not as precise, of course, but how much did we have to do? Once we had the model, just needed one addition. So if you are saying we need to be able to calculate this over and over again, using this model that just takes one addition will save you a lot of time over using this one that takes 4 multiplications. And it's even more multiplications if you need more decimals. So this is what approximation is all about. We're having a trade-off between how fast your model goes and how accurate it goes. And you can say, I'm willing to give up some accuracy in order to make it go faster and be easier to work with. Okay, so there's one other topic, and it's called differentials. And this is mostly a notational trick. It's not really that different from the tangent plane, but it's saying as we move away from the anchor point, we can lose accuracy, but we say how far off does it change? If we let x go to x naught, when it's very small, we write dx. As y goes to y naught, it's very small, we write dy. And what this means is that we are letting these be incredibly small, and it can give us, if there's a very small change in x and very small change in y, we can figure out what the change in z is. And so what happens here, this is also the chain rule, which you'll see is like, we want dz, we do del z over del x times dx, and del z over del y times dy. These are partial derivatives, but these sort of cancel out, so we get partial z plus partial z equals total z. So this is how you have to do it. You have the independent variables x and y, so you take the derivatives and you multiply them by little dx and dy. And what it means is that if you plug in a change, a small error, a small variance to x and y, you can get the amount of variance in z. So, like I said, a lot of this is just a notation trick. So let's do this example. I think it's fairly straightforward. Find dz. So we say del z over del x is 2x plus 3y. And del z over del y is 3x minus 2y. So then dz is del z over del x times dx plus del z over del y times dy. That means it is 2x plus 3y dx plus 3x minus 2y dy. And then if you have an anchor point, you would plug in the anchor point to regular x and y, and then you would have what's basically the tangent plane there, but centered at no change, so that you're only plugging in the change of values instead of the actual position. You also might write this as delta z is approximately 2x plus 3y delta x plus 3x minus 2y delta y. And again, it's notation. The idea is that d, the little d, are limits, and so they're exact because we had to take all the way to infinity. In real life, you'll be using actual measures, which are not all the way to limit to 0. So you'll plug in numbers, you'll get another number out. And it won't be exact, but it'll be pretty close, as long as these are small. Let's do an example, because I think it'll be a lot more clear once we see an example. I mean, that was kind of an example, but let's do an actual verbal example. So, the base radius and height of a right circular cone are measured as 10 centimeters and 25 centimeters, respectively. The possible error in measurement of as much as epsilon centimeters in each one. So we take a ruler or whatever, and we measure these lengths. The measurement is probably not exact. It's probably some error in there. We say the measure we got was 10 and 25. And so I want to know, well, if that's how far off the radius and height were, how far off was the volume? And then For instance, if the error of each individual one is as much as 0.1 centimeters, how much could the volume be off by? And it makes sense, an error in radius is probably more important than error in height because the radius has a square in it. So let's work out what the formula here would be. So del V over del R, this is the formula for volume, and these problems assume that you already know the formula for volume and of various shapes. So we get 2 pi r h, and del V over del H is pi r squared. In this case, the anchor point is our measurement. Because we have no better estimate than the thing that we actually measured, so we might as well anchor it there. If you were taking statistics, they would call this a point estimate, meaning there's some error involved, but we're going to say as the default assumption is that our measurement was right, and then allow a little bit of error. So dV would be 2 pi RH dr, this one had the r, plus pi r squared dh. And now let's plug in our anchor. We measured r equals 10 and h equals 25. So this would give us 500 pi dr plus 100 pi dh. Now if we say our ruler is off by an epsilon, so we say if dr and dh are both less than epsilon, then dv is going to be less than 500 pi epsilon plus 600 or plus 100 pi, or 600 pi epsilon. So the error is less than 600 times pi times whatever the individual errors were, and it would be centimeters cubed because it's volume. So for instance, if epsilon is 0.1 centimeter, like they said, our ruler is such that it could be off by as much as 1/10 of a centimeter. Then we know the volume error it's got to be less than 600 pi times 0.1, or 60 pi centimeters cubed. Okay, let's do one more. It's very similar, just uses a different shape. So, dimension of a rectangular box are measured to be 75, 60, and 40. Length, width, height. You could switch them around, I suppose. It doesn't really matter what you call them. But do the exact same thing. Find the largest possible error when the volume is calculated from these measurements that are off by as much as epsilon. And then what if epsilon is 0.2 centimeters? Alright, so what is the volume of a box? It is length times width times height. So we need to get our partials. Del V over del L is WH. Del V over del W is LH. And del V over del H is LW. Our anchor point was 75, 60, and 40. So this gives us 2,400, 3,000, and 4,500 as our partial derivatives. So we need dV. Now since there are three variables this time, it's del V, del L, dL, plus del V, del W, dW, plus del V, del H, dH. Same process, just one extra dimension to take care of. So that would become, let's see, looking back up, Del V del L was WH, so 60 times 40 is 2400 DL. Plus del V del W was L and H, which comes out to 3000 dW. And del V del H was L times W, which would become 4500 dH. Now, if we say dL, dW, and dH are all less than epsilon, and it could be that the three measures had different errors, but in this case we're saying they're all no greater than epsilon. So we would get dV is less than, add these together, you get 9900 epsilon. So that's the error in volume is less than 9900 epsilon times centimeters cubed. Or centimeters cubed. So if, as they suggested, your ruler is calibrated so that every measure is off by less than 0.2 centimeters or 1/5 of a centimeter, then volume error is less than 9900 times 0.2 or 1980 centimeters cubed. So yeah, if for instance you measured it and you got a thing and it said it was you estimated it was 1,000,000 centimeters cubed, you know that the actual value is between subtract 10 to the 6 minus 1980 and 10 to the 6 plus 1980. That the actual value is somewhere between there because there's your estimate plus or minus the error. All right. Thank you.